The URL shortener is a staple of the system design interview. The objective is to take a complex web address and condense it into a unique shortened code. A basic implementation requires only a single server and an in-memory hash table. You generate a random string, map it to the original URL, and the service is functional. This system is governed by two constraints. Shortened links are immutable, meaning they cannot be edited or deleted, and the codes must remain as short as mathematically possible. A production environment requires high availability and strict fault tolerance to handle millions of simultaneous users. Relying on a single router or server creates a single point of failure. If that central component goes offline, it stops the entire system from working. Global traffic volume transforms this string manipulation task into a complex problem of distributed architecture. We begin with the requirements. The system must generate 100 million new URLs every day. 100 million URLs divided by the 86,400 seconds in a day results in a write throughput of approximately 1,160 requests per second. This is a read-heavy system. With a 10-to-1 read-to-write ratio, the infrastructure must support 11,600 redirects every second. Over 10 years of operation, the storage layer must accommodate 365 billion total records. This table shows the relationship between character length and capacity. Using a base 62 character set, numbers and letters, a 7-character hash provides 3.5 trillion possible combinations, which covers our 10-year projection. At this scale, sub-millisecond read latency is the critical metric for the entire project. The system requires two primary REST-style API endpoints, a POST request to shorten a long URL and a GET request to handle the redirection. When a client visits a shortened URL, the request hits the shortening server, which returns a location header pointing to the original long URL. An HTTP 301 redirect indicates the URL has moved permanently. The browser caches this response, so subsequent clicks bypass our servers and go directly to the destination. This reduces infrastructure load but prevents us from tracking click analytics. An HTTP 302 redirect is temporary. The browser sends every click to our service first, allowing for precise tracking at the cost of higher server traffic. The choice between 301 and 302 is a strategic decision between maximizing infrastructure efficiency or maintaining business intelligence. We store these mappings in a relational database. The schema includes an auto-incrementing ID as the primary key, the shortened code, and the original long URL. One method for generating codes is to use hash functions like crc32 or MD5 and truncate the output to 7 characters. Because we are truncating the hash, collisions are inevitable. As shown here, the system must check the database for existing entries. If a collision occurs, it appends a string to the URL and rehashes until it finds a unique value. A second approach is base 62 conversion. This uses the 62 available characters in our alphanumeric set to represent the database ID. The conversion process uses a series of divisions by 62. For example, the base 10 ID 11,157 produces remainders that translate to the base 62 string 2tx. This comparison highlights the trade-offs. Hashing is independent of the ID, but requires collision resolution. Base 62 is deterministic and collision-free, but its length grows as the ID increments. Pairing base 62 conversion with a distributed unique ID generator creates a collision-free architecture that scales to billions of records. The shortening flow begins by checking the database for the input URL. If it is new, the system generates a unique ID, converts it to a short URL, and saves the new record. The unique ID generator is the central state management component, ensuring every worker server in the cluster receives a globally unique identifier. To maintain high performance on the read path, we introduce a cache layer between the web servers and the database. As the cache reaches capacity, eviction policies like least recently used, or LRU, remove the oldest data to make room for new redirects. This cache layer intercepts the majority of requests, preventing the 11,600 redirects per second from saturating the relational database. The final architecture integrates a load balancer to distribute traffic across a fleet of web servers, which then coordinate between the cache and the database. Keeping the web server stateless allows for horizontal scaling. We can add or remove server capacity based on real-time traffic volume. To store 365 billion records, the database layer must use master-slave replication or sharding to maintain performance across multiple physical nodes. A rate limiter is implemented to prevent malicious traffic from exhausting system resources. We use a content delivery network to cache static assets. CDN servers geographically close to the users deliver content faster than the origin server, further reducing latency. Designing a URL shortener requires balancing unique ID generation, deterministic encoding, and tiered caching strategies. The next challenge involves shifting from URL shortening to active discovery. We will design a web crawler capable of managing a massive URL frontier and deduplicating billions of pages across the internet.